Thank you very much for the introduction. My name is Choi, and I'm currently working in professional management. Today, I will talk about polymer-coated silica with a high color factor microresonators. Even this device uses silica microtroid. As a platform, the optical response will be quite different compared to monolithic silica microtroid. So we would like to call this device as hybrid optical microresonators or hybrid devices during the presentation. For the outline, I will be talking about background and motivations to cover visible gallery mode and color factor and its potential applications, and theory and experimental results, and finally conclusions. The concept of visible gallery mode is coming from the sound effect that Lloyd Rayleigh observed the sound propagate around the interior gallery of St. Paul's Cathedral, where one can whisper around the world and can hear all of the parameter of the dome. As some type of optical microcavities show same behavior when covered light into the cavities, we call this device as visible gallery mode types optical microresonators. For visible gallery mode types optical microresonators, the light is coupled into the cavity when the waveguide and optical microresonators have index match, and the light propagated by polar internal refraction for a certain amount of time in the cavity. This geometry optics shows the light, the resonance only occurs when the light propagated by integral fashion, and the other case it is off resonance. Due to its exceptional mode of confinement in visible gallery mode types of optical microcavities, people have found various functional applications, various potential applications, such as narrow lineless laser, biochemical detection, mechanical oscillators, and cavity quantum electrodynamics, and other dark filters. These types of potential applications have been demonstrated in the laboratory. So color factor, which describes the series of loss mechanism in the cavity, is important parameter as it is related with the sensitivity of the devices. To measure color factor, one method is line-width measurement. In this case, color factor is defined as resonance wavelength divided by width half maximum of the resonance. And the other method to measure color factor is cavity ring-down measurement. In this case, color factor is defined as frequency times photon light time in the cavity. To measure photon light time from the cavity, we send a single pulse of optical signal into our optical microcavities. Then we shutter to shutter, and we can get the value of photon light time from the exponential decay. In our research group, we use line-width measurement to characterize our optical microcavities. So this slide shows different geometries of visible gallery mode types of resonators. The left picture shows microtroid and micropulse, microsphere, and the middle picture shows the resonant microdisc, and the right picture shows flat microdisc or microring. Among these geometries we use in our research group, we are focusing on microtroid, microsphere, and resonant microdisc. For the research that we are presenting today, we call the polymer on silica microtroid to study its loss mechanisms in the cavity. For the motivation of studying hybrid devices, we can study various functional polymers such as chemical-specific, light-emitting, negative thermo-optic, electro-optic polymers. These types of polymers has not been intensively studied by using optical microcavities, so it is an interesting area to study for future research. To fabricate our devices, we first start with 2 micro-thick oxide layer on silicon substrate to make the circular pattern by standard photoresorption to make the silica pad. Then we use xenon diphoric acid etcher to selectively etch down silicon underneath of silica to make silica microdisc. At this point, color vector is 10⁶, limited by surface scattering. Then we use carbon dioxide laser to make the silica microtroid. At this point, color vector is 10⁸, limited by internal scattering. For the research that we are presenting today, we call the polymer on silica microtroid to study its loss mechanisms for hybrid devices. So color vector describes a series of loss mechanisms in the cavity. These loss mechanisms are material surface scattering, coupling, radiation, contamination losses. We can easily minimize the surface roughness by using the Pro process for making optical microcavities, and we use low-loss tempered optical waveguide to populate into our cavities to minimize the coupling loss. And in addition, we can minimize radiation loss by using large enough optical microcavities, as it is related with the critical angle of total internal reflection, which can be defined by a refractive index of optical microcavities and its surrounding area. Viewers can minimize contamination losses easily by keeping optical microcavities in clean conditions. So color vector for hybrid device can be assumed to be material loss limited, as all other loss mechanisms in the cavity can be minimized by the method previously mentioned. The analytical form of material loss limited color vector is shown here, where n sub EFF is effective reflective index of the system, and alpha sub EFF is effective absorption coefficient of the system. The sum of beta gamma delta should be 1, as beta gamma delta describes percent of optical field in each material. To verify this hypothesis, we determined the color vector through a series of theoretical calculations and experimental measurement using two polymers, polystyrene polymer acrylate, and all measurement and calculations were performed at two wavelengths, 850 and 980 nanometer. For theoretical study, we use conserved multiphysics, which is finite element analysis software for modeling and simulations of any physics-based systems. In this slide, we can see a same image of fabricated silica micro Choi and film result of silica micro Choi and 100 nanometer, 200 nanometer thick polystyrene hybrid devices at lambda equals 850 nanometer. This optical field distribution is corresponding to a highlight region on this drawing, and it is important to recognize from this film result there is optical mode shift, mode shape change with a polymer coating, because the polymer with a higher refractive index than silica acts as percolating layer. So we modeled a series of simulations by changing major, minor diameter, and film thickness. As a result, we found that film thickness has the greatest effect on color vector. So this graph shows the percent of optical field in polymer layer as a function of film thickness with two different polymers and with two different wavelengths. By using this calculated percent of field in each region, and by using this equation, we can calculate theoretical material loss limited color vector. So this slide shows the film result for PMMA hybrid devices, as color vector is highly dependent on percent of optical field in polymer layer, because the higher is absorption loss than silicon air at both wavelengths. These graphs are drawn by systems. As you can see, there is two y-axis. One is color vector on the left, and the other one is percent of optical field in PMMA layer, and x-axis is PMMA thickness. Color vector is highly dependent on PMMA thickness because percent of optical field in PMMA layer also changes with PMMA thickness changes, and the percent of optical field in PMMA layer is highly dependent on PMMA thickness because there will be more optical field squeezed between silicon air with a thicker coating of PMMA, because the refractive index of PMMA is higher than silicon air at both wavelengths. To summarize, the loss of PMMA is silica higher than silicon air at both wavelengths. As the thickness of PMMA increases, the color vector decreases. This slide shows the film results for polystyrene hybrid devices. Same explain goes here as PMMA hybrid devices. One difference is that as the refractive index of polystyrene is higher than PMMA, there will be more percent of field residing in polystyrene layer compared to PMMA layer and same coating thickness. To summarize, loss of polystyrene is higher than silicon air at both wavelengths. As the thickness of polystyrene increases, the color vector decreases. For testing, we use narrow line-based continuous wave tunable laser to scan optical signal, and the light passes through attenuator where we can control input power. And the interaction of waveguide and optical microresonators can be sensed by a photodetector and can be monitored high-speed digitizer on computer. In addition, we use function generator to modulate scan speed and scan range. This left graph shows a breadth scan of hybrid devices with a free spectral range of 3.5 nanometer, and the right one shows fine scan of the resonance. So this slide shows comparison for measured and calculated color factor as a function of PMA thickness for PMM hybrid devices. As you can see, there is good alignment between theory and experiment. So as the thickness PMA increases, the color factor decreases at both wavelengths because loss of PMA is higher than silica and air. This slide shows comparison for measured and calculated color factor as a function of polystyrene thickness for polystyrene hybrid devices. As a result, there is a good alignment between theory and experiment. So as the thickness of PS increases, the color factor decreases at both wavelengths, and loss of polystyrene is higher than air. For conclusions, we developed material loss limited color factor model using finite element simulations, and we fabricated hybrid silica polymer microcavities using polystyrene and polymetallic metal acrylate, and we demonstrated that the material limited color factors with polymer-coated microcavities, which color factor is over than 10 to 7, and we demonstrated that nanometer scale changes in the film thickness will change in the optical field profile. I would like to thank our advisor, Professor Andrea Armani, with her great direction for the research, and Xiaomi Zhang, who is the co-author for this research, and rest of our group members. This research is supported by ARL and ONR, and presentation slides will be available on our Google page on the slide. Thank you very much for your attention, and I'm ready to take questions.
We have a few minutes for questions, so fire away.
What do you do to reduce the surface loss? You said the surface roughness loss is eliminated by some process. I just didn't notice here. What is that?
Oh, okay. So,
yeah.
You mean this one?
No, the next slide, there's a cue for
Next
surface
slide.
roughness, and you said you're going to eliminate it by.
Oh, okay. So because of during the fabrication, when we make silica microdisc, we use xenon diaphragm gas etcher. So we use gas ion to etch silicon. So it affects the surface roughness during the etching process. But after we use carbon dioxide laser to make the silica microtroid, the surface lostness can be minimized because it can smooth the surface.
What is the effects that using polymer that decreases color factor?
Oh. Even though it decreases color factor, one advantage is we can move this optical field to strong area to polymer layer, and also by moving the optical field in strong optical field in polymer layer, we can study this kind of polymers photosilica microtroid, and we can make a strong interaction of the field in the polymer layer. So we can make, by using this kind of, for example, if we use light in polymers, we can make optical field a strong interaction in the polymer layer and can make maybe low loss lasers, something like that.
All right, let's take the speaker once more.